Hello, welcome to the second part of optics. My name is Opak Mark, a physics and mathematics teacher. In this second part, we are going to look at refraction through lenses, and then we shall look at the optical instruments. So in this lesson, let us look at the types of lenses, the terms used in lenses, and then images formed by convex lenses. So what is a lens in itself? A lens is a glass bounced by one or two spherical surfaces. Let's look at the types of lenses. There are mainly two types of lenses, that is the convex or the converging lens, and also we can define this as a lens which is thicker in the middle than at the edges. Then the second type is the concave or the diverging lens, which is thinner in the middle than at the edges. Now you realize that for the convex lens it is converging, but when we are looking at mirrors, convex mirror was actually diverging and concave mirror was converging. But in this case, concave is the diverging lens. Let's look at this illustration. So here we have what we call the biconvex lens. So it's called bi because both surfaces are convex. And then you also have what we call the plano-convex, where one side is flat, one surface is flat, the other one is convex. Then you also have what we call the converging meniscus or the convex meniscus, where we have this being convex and then this being concave. Let us also look at the second illustration here. We have here this other illustration where we have the biconcave. Biconcave, both surfaces are concave, and you can see it is thinner in the middle. That is the concave lens. This is the concave lens or the biconcave lens. Then you have what you call the plano-concave, where one surface is flat, then the other is concave. That is plano-concave. And then the diverging meniscus or the concave meniscus is convex, and then this is concave. This is concave. Let's look at the terms used. So I have C1 and C2 here. These are the centers. These are the centers of the lens surface. Remember, we get the lens from two spherical glasses. So that's how we form this lens. So this is the lens surface, and then this is the lens surface. So these are the centers of the lens surface. So let us define the centers of the curvature of the lens. Center of curvature of the lens. And the center of curvature of the lens, we can define it as the center of the spheres of which the lens surfaces forms part. And then also let us define the radii of curvature of the lens. The radii of curvature of the lens. The radii of curvature of the lens is these are the distances from the centers of the surfaces of the spheres of which the lens surfaces forms part. Yeah, it's the distance of the centers of the surfaces of the spheres of which the lens surfaces forms part. Now let us also look at the principal axis of the lens. Principal axis of the lens is the line joining the centers of curvature of the two surfaces of the lens. Let us also define the optical center of the lens. Optical center of the lens, this is the midpoint. This is simply the midpoint. This is the midpoint of the lens surfaces. This is the midpoint of the lens surface through which actually the rays pass undeviated. Or is the incident rays pass undeviated. Through which the incident rays pass undeviated. Then let's also look at the paraxial rays. Remember we talked about paraxial rays when you're looking at mirrors. So the paraxial rays, these are rays which are close These are rays which are close to the principal axis and make small angles with the lens axis, Let's also define the principal focus, capital F, of a convex lens. So this is a point on the principal axis where rays originally parallel and close to the principal axis converge after refraction by the lens. And for a convex lens, usually the principal focus is real. Then let's also look at the principal focus, capital F, of a concave lens. For a concave lens, this is the point on the principal axis where paraxial rays incident on the lens and parallel to the principal axis appear to diverge from after refraction by the lens. And for a concave lens, it is virtual. If you talk of virtual, means that it is behind. The principal focus is behind. It is virtual. Let's also look at the focal length F. This is supposed to be a small f, not capital, small f, of a convex lens. The principal focus of a convex lens. So we shall define this as you can define it just like the distance from the optical center. You can define it as the distance from the optical center to the principal focus of the convex lens. Or if not, you can define it as the distance from the optical center, to the point where, on the principal axis where paraxial rays incident on the lens and parallel to the principal axis converge after refraction by the lens. And then also we have the focal length, small f, of a concave lens. This is the distance from the optical center of the lens to the point where paraxial rays incident and parallel to the principal axis appear to diverge from after refraction by the lens. Now, let us also go ahead and look at the geometrical rules for the construction of ray diagrams. So these are the rules, these are the rays that you're going to be following when we want to locate the image position. So we shall follow this set of rules in order to locate the image position. So the first rule here, we are going to look into all the what we sometimes call the principal rays, is that a ray parallel to the principal axis, is refracted and passes through the principal focus or appears to pass through the principal focus. That is in the case of a convex, in the case of a concave lens. And then also we have the second, is that a ray passing through the optical center, a ray passing through the principal focus, is refracted parallel to the principal axis. A ray passing through the principal focus is refracted parallel to the principal axis. And then also the other one is what I talked about, that a ray passing the optical center or passing through the optical center, that is the optical center C, is not deviated, or it is not refracted. And now let us look at this for a converging lens. A ray parallel to the principal axis is refracted through the principal focus. A ray passing through the principal focus is refracted parallel to the principal axis, and a ray passing through the optical center C is not refracted, it is undeviated, it just continues in a straight line. Now let us look at this note, let us make some note here, that the normals to the lens surfaces must pass through its centers of curvature. I think this is quite similar to what we talked about when you're looking at mirrors, that any normal to the lens, passes through the centers of curvature. Then also we need to make a note that the images, the image position can be located by the intersection of two refracted rays initially coming from the object. So we shall draw all our rays from the object, and where the two rays meet, because you usually use at least two rays, where the rays intersect, that's where the image will be formed. So let us look at the images formed by a convex lens. So the nature of the images formed by a convex lens depends on the position of the object from the lens. Let us look at this. When the object is between F and C, that's between the focal point or the principal focus F and the optical center. This is the optical center. So in this case, this lens will be working as a magnifying glass. Let us see that. So you're going to place your object between F and C, and then you draw a ray parallel to the principal axis. It's refracted through the principal focus. This is a ray. There's an arrow missing here. You need to include that arrow. A ray. And then also a ray that passes through the optical center goes undeviated. And then when you produce the lines, they meet at this point. And that is going to be a virtual. As you can see, the nature of the image is going to be virtual. It is going to be upright, that is erect, and it is going to be magnified. Let's look at when the object is at F. When the object is at F, this is what you're going to be having. So a ray parallel to the principal axis is refracted through the principal focus. A ray passing through the center of, the optical center, a ray passing through the optical center goes undeviated. A ray passing through the optical center goes undeviated. And so you'll find that these images, these two rays are going to be parallel. They're going to meet at infinity. We say it is going to be meeting at infinity. So okay, they are parallel, so we shall say that the image is going to be formed at infinity. So the nature of the image is that it is formed at infinity. Let us also look at when the object is between F and 2F. When the object is between F and 2F, you place your object between F and 2F. Remember, the distance from C to F is the same as the distance from F to 2F. The distance from C to F is the same as the distance from F to 2F. So when the object is placed between 2F and F, a ray parallel to the principal axis is refracted through the principal focus. A ray passing through the optical center goes undeviated, and the image formed is going to be real. It's going to be real. Remember, I defined a real image as an image formed by intersection of actual rays, and they can be formed on the screen. So in this case, the nature is real. You can see it's also inverted, and then it is magnified and formed beyond 2F. Let's also look at when. Let's look at the case when the object is at 2F. When the object is at 2F, you are seeing at 2F, a ray parallel to the principal axis is refracted through the principal focus. A ray passing through the center, that is the optical center, goes undeviated, and it meets at this point. These two rays meet at this point, and therefore the nature of the image is going to be real, as you can see. It's going to be real, it's going to be inverted, it's going to be the same size as the object, and then it is going to be at 2F. Let's look at the image when the object is beyond 2F. When the object is beyond 2F, so when we place our object beyond 2F, this is what you're going to be having. When the object is beyond 2F, a ray parallel to the principal axis. Remember, all our rays must be drawn from the top of the object. A ray parallel to the principal axis is refracted through the principal focus. and a ray passing through the optical center goes undeviated, and the nature is going to be real. We can see it's going to be inverted, it's going to be diminished, and then it's going to be between f and 2f. Let us look at when the object is at infinity. So if the object is at infinity, we shall draw rays from infinity. So let's draw some two parallel rays from infinity. This time round, this ray is not parallel to the principal axis. So we shall draw this ray, and that will be, it will undergo conversion here till the refraction is going to take place, so it's going to converge. And then also a ray passing through the optical center goes undeviated. So where the two rays meet is where the image will be. And this time around the image will be at f. Image will be at f, and it is going to be real, and it's going to be inverted and formed at f, and also diminished. Let's make a note here. Generally, the image of an object in a convex lens is virtual only when the object is nearer to the lens than its focus. So if it is nearer the lens, so we can see this is usually when actually it is placed between C and F. But whenever it is far away from the principal focus, then it is going to be real. Let's look at the uses. Remember, we looked at a number of uses when we are discussing the mirrors. So for the lens also we have a number of uses. These lenses also have a number of uses which we're also going to be looking into. So what are some of the uses of these lenses? We are going to see that these lenses, they are used in spectacles. They are used in spectacles. They are used in spectacles, especially to correct. They are used in spectacles to correct. They are used in spectacles to correct long-sightedness, or they are used in spectacles for long-sighted people. They are used in spectacles for long-sighted people, and then they are also used in cameras. They are used in cameras, and they are used in projectors. They are used in microscopes, and then they are also used in astronomical telescopes. Thank you for your attention. We meet in the next lesson.